Hello, I'm Miss Ginsburg with KnowAtom, and today we're going to be reading Matter and Sound. This is a student reader in Unit 8. Sound is energy. Slamming a door. There is a mausoleum in Scotland where the sound of a door slammed with enough force will echo for 15 seconds. Mausoleums are structures that hold burial chambers. Sound is energy that is carried in waves by vibrating molecules. To vibrate means to move back and forth quickly. When you slam a door, you transfer kinetic energy to the door. When the door collides with the door frame, the door transfers energy to the door frame. This collision causes the molecules that make up the door and door frame to vibrate. Some of the kinetic energy is converted to sound. The energy from the door slamming causes nearby air molecules to vibrate and bump into molecules closest to them. This passes on the energy and makes them vibrate too. Then those molecules bump into more particles and so on. Particles stop vibrating once they have passed on the energy. How sound travels. When you slam a door, the sound travels outward from the source. It is carried in sound waves, which are patterns of vibrating molecules caused by movement of sound through a medium. A medium is the matter a wave travels through. It can be solid, liquid, or gas. Sound travels through the molecules of air that fill the room. If you are within the range of these vibrating molecules, your ears pick up the vibrations and hear them as the sound of the slamming door. The farther away you are from the source of the sound, the quieter the sound seems. Because sound energy is transferred from molecule to molecule, sound waves cannot travel in a vacuum, where there is no matter. It is important to note that waves don't carry matter. Molecules stop vibrating and return to their original position once they have passed on the energy. Movement of a sound wave. Sound waves are called longitudinal waves. They are caused by the back and forth vibration of the molecules of the medium. If a sound wave is moving from left to right through the air molecules will vibrate to the right and left as the energy of the sound wave passes through it. A transverse wave is the other kind of wave. In a transverse wave, if the wave moves from left to right, the disturbance moves up and down. When a crowd of people in a stadium do the wave, they are modeling a transverse wave. The individual people move up and down while the wave moves from left to right or right to left. After the disturbance passes through, the people go back to where they were before the wave moved through. Parts of a sound wave. As sound energy moves through matter, it causes molecules to press together. This is called compression. When this happens, the molecules on either side of the compression spread out. This is called rarefaction. In some waves, the molecules become more compressed than in other waves. This has to do with the wave's amplitude. Amplitude is a measure of the wave's displacement from its resting position. Displacement refers to the movement of a substance from its resting position. The larger the force is that causes the disturbance, the greater a wave's amplitude will be. Because of this, amplitude is related to the amount of energy a sound wave carries. The greater the amplitude of a sound wave, the more energy it is carrying and the louder it will be. The loudness of sound is measured in decibels. If you gently close a door instead of slamming it, air molecules don't become as compressed because you apply less of a force. This means there is less energy, which results in a quieter sound. In a sound wave, the distance from one compression to the next or from one rarefaction to the next is the wavelength. In other words, the wavelength is the distance spanned by one cycle of the motion of the wave. The frequency of a wave is the number of waves that pass a set point in a given amount of time. Frequency is closely related to pitch, which describes how high or low a sound seems. A sound wave with greater frequency has a higher pitch than a sound wave moving at a lower frequency. A whistle is an example of a high-pitched sound. The sound waves produced when you blow into the whistle have a high frequency. A door slamming is an example of a low-pitched sound. The sound waves produced when you slam the door move at a slower frequency. How sound interacts with matter. If you are in one room and you hear a door from another room slam, it means the sound has been transmitted through the air. To transmit means to pass from one place to another. In order for there to be an echo, the sound waves have to come into contact with a reflective material. To reflect means to bounce off of something. Sound waves are reflected when they collide with matter that acts as a barrier. Echoes can only happen in large spaces. Sound moves very quickly, but it still takes time for the energy to move from one place to another. Echoes happen when there is a break between when you hear the original sound and when you hear the reflected sound. Finally, the sound needs to be loud enough so that it has enough energy to move through the large space and back. In the mausoleum, the sound waves produced by the slamming door were transmitted through the air. They traveled until they reached the hard, reflective walls and high domed ceiling. They were then reflected off of the surfaces and produced the 15-second echo. Controlling sound. Renovating a concert hall. Jordan Hall is part of the New England Conservatory located in Boston, Massachusetts. It is considered one of the United States' best performance spaces because of its acoustics. Acoustics is the properties of a space that determine how sound waves travel. It is important when designing buildings such as auditoriums, theaters, and libraries. In 1995, Jordan Hall was renovated. To renovate means to make repairs. These renovations were done carefully to keep the acoustics of the hall. No structures of the room were changed that might affect how sound was carried. But the first night musicians played after the renovations, the music sounded different. Many people said it sounded too bright. Some audience members covered their ears with their hands. This is a picture of Jordan Hall. How materials absorb sound. It turned out that the new paint may have had a role to play in the changed sound. The new paint wasn't as porous as the old paint. This means it didn't have a lot of spaces between its particles. It's possible the new paint was much more reflective than the old paint. As the musicians played, their instruments made vibrations. These vibrations moved through the air in sound waves. As the waves came into contact with the painted walls, they were reflected back. The more porous paint absorbed more of the sound waves. To absorb means to take in. When a sound wave is fully absorbed into a material, all of the sound energy transfers to the material and is changed to another form, such as heat. When this happens, no sound is transmitted through the material. Many materials absorb some, reflect some, and transmit some sound energy. It depends on the properties of the material, including how porous it is and how thick. When sound waves are partially absorbed and partially transmitted, some of the sound is carried through the material, but it isn't as loud because some of the energy has been converted to another form. Acoustics of a room. The old paint of the concert hall absorbed more of the sound waves than the new paint did. This resulted in a softer sound. After a year, the concert hall added felt cloth to its walls. This returned the acoustics to the previous sound because felt is more absorbent than the new paint. In general, softer, rougher materials tend to be more absorbent. Harder, smoother materials tend to be more reflective. Concert halls like Jordan Hall are designed so that everyone in the room can hear the music. One way these halls achieve this is their shape. They are often designed with many curves that move the sound around the room. Concert halls also have carpet to absorb sound energy. This transfers the sound energy into heat and prevents echoes. Libraries have a different acoustical design goal. Libraries are designed to keep sound from traveling to help them stay quiet. I learned a lot reading Matter and Sound, and I hope that you did too. I'll see you tomorrow with another one. Bye.